So welcome everybody. I guess we can start for tonight or for this morning in US. So the speaker of today is Tommaso. I guess most of you know him. He's a PhD student. He's almost finishing his PhD program in KU under the supervision of Professor Rayon. And well, he worked at CERN in the totem and CMS PPS experiments. He was actually one of the expert that developed what we call the double diamond. So basically using two diamonds, a sandwich of two diamonds instead of one single diamond as a timing detector. So since he started his research career not too long ago, luckily for him, he's still young, he started working on timing detectors. Now we will talk today about some application of timing detector, but not to high energy physics. So the idea is to take technology developed for the LHC and use it for something that could be useful for, in this case, for medical application, for medical facility. So without any further ado, I leave the field to you.
Thanks a lot for the presentation. You actually cover everything that I wanted to say. So yes, here today we're gonna talk about the application of low gain avalanche diodes, or LGADs. They're usually used for fast timing applications in high energy physics experiments, but in medical applications. And as Nicola already said, it's not probably my field, but it's this side project that we had with Professor Christophe Royon then became really an important part of my research path here at KU. For any further information about the data that I will present, you can follow this URL over here, and you're going to find the paper that just been submitted. So let's go through the outline for a second. I decided to divide in 3 parts my presentation. In the first one, I'm going to give you a brief idea of, or a general overview, if you want, of the method of detection and timing detection that we use. I'm going to expand a bit over the readout front end and post-processing procedures that we use for obtaining our results. In the second part, I'm going to talk about the collaboration with so the actual core of the presentation, the collaboration with the University College Dublin and the St. Luke Hospital to set up a week of test beam using a medical facility. And in the last part, I'm going to use just some of your time to summarize some of the possible next step in application of low gain avalanche diode outside high energy physics. So let's start with the timing detectors. So first of all, a general overview over detections in general. A particle detector is basically a transductor, so an object that converts a certain physics quantity in another one. In this case, it converts the energy released by the passage of a particle through its active volume, and it converts it basically in an electric signal, in a current that we can detect and study. So here on the right side of the slide, we can see a general basically principle of operation of a particle detector. In this case, there are infinite type of detector that I could describe, but here I'm describing a solid state detector. Here we have the sensor, so the active area, or the transductor that transforms the energy in current. And this current is then read and processed by an amplification and shaping chain that is commonly named Readout. And the last stage is just it's usually in our case, at least for timing application, a sampling and recording of the signal by the use of fast high bandwidth sampler. And after that stage, clearly, we obtain our raw data that can be analyzed. And embedded in the signal that we obtain at the end of this chain, there is a bunch of information that we can extract about the particle that is passing through the sensor itself. It can be the momentum, the mass, the energy, depending on the technology that we are using. But if we want to focus for a second on timing detector, what is the definition of a timing detector? Well, there are many definitions that we can use. In this case, I just summarized two that we're gonna use during the presentation. In the first half of this slide, you can see that the time detector indicates a class of devices that are optimized to reconstruct the timestamp of the passage of a particle through the volume. That means, what does that mean? That means that the goal of the timing detector is precisely reconstruct the time which the particle passed through the volume itself. In the example over here, we have two devices, D1 and D2, and a single particle passing through both of them and generating a signal of start and stop. And you can see that the distance between the two devices can be linked just to the time information if we know the velocity of the particle itself. But more important, the uncertainty of the measurement depends only on the uncertainty of the time reconstruction of the devices. Also, clearly depends on the number of independent measurements that I perform of the same event. So in this case, we talk about precise detectors. So what is a precise detector? A detector that up to a precise timestamp of the passage of a particle, and is suited for time of flight application, different time of arrival, and can be used as a really good time reference for high energy physics experiments. New generation particle detectors can go as low as 10 picoseconds, tens of picoseconds of time resolution, and this time resolution can always be used to reconstruct an accuracy in this spatial measurements. But a different definition can be time detector refers to devices that are designed to instantaneously react to the passage of a particle. That means that if you see the example over here, our detector detect the passage of a particle, and the output is a really narrow peak. That means that the dead time of the system is going to be really small. So the system is going to be able almost instantaneously to react the passage of a second particle. So what is a fast detector? Well, it's a detector output a narrow pulse in response to the passage of a particle, what I was just describing. And the motor components, electronic components it can use can be used to develop circuits that can output signal that are fast as a few nanoseconds. So we reduce the integration time, we reduce the dead time, and we can use the particle detector as a single quantum, basically, a detector. Up to, you'll see later, up to high rates. So what is the first step in developing a detector? For sure is the choice of the sensor. So the quality of the sensor, the production process, and the material used somehow decide the performance of the detector and influence all of the properties of the resulting detector. For example, the charge collection efficiency, that is the ratio between the charge generated in the bulk and the charge that are actually collected in the electrodes. The radiation tolerance, that it's an important factor in many high energy physics experiments. And also, if we have, like you will see in low gain avalanche diodes or in LGADs, the gain due to the multiplication process of the charges in an eventual gain layer. So over here on the right, we can see the scheme of a simple sensor that is plugged to a polarization circuit that provides electric field inside the bulk that is needed to drift the free charges towards the electrode and generate the current that is then collected by the readout. We'll focus only on solid state sensors, even if other technologies are used for timing purposes, but these are the ones that are going to be needed for this presentation. And solid state sensors has a really high mobility. That means that and really high saturation velocity. That means that the carriers inside the bulk can move really fast, and the rise time of the signal will be really sharp. Then we can talk about the capacitance of the sensors that is decided by the dielectric constant in this case, and it's going to decide how to adapt basically the sensor to the readout. And then some other properties, such as the displacement energy that is related to the radiation tolerance, is the lowest energy needed to actually create defects inside the sensor. Now, going to the technology that we are actually interested in, those are called LGADs, low gain avalanche diode. And this is a technology that during the last decade show incredibly promising results and has been heavily exploited in the design of timing detectors for high energy physics experiment. So what are some properties of the LGADs? What are some features of the LGADs? So as the name says, it has a low gain. And this is not a bad thing. Low gain compared to what? Low gain compared to a normal PIN diode, so an avalanche photodiode. The low gain acts in like has a contain, let's say like this, has the functionality to contain the avalanche process, so to help the rise time being sharper. But we need to add an additional gain layer that in these pictures in blue over here to recover the signal to noise that we are losing due to that. Even if although the sensor thickness can be reduced to down to 50 microns, 35 microns, down to tens of microns, the dark current can be pretty small. Also, the radiation tolerance, as I said before, due to the strict requests of a high energy physics experiment, can be drastically improved, using some insertion in the crystal of the bulk itself. Some of the main, producers are listed over here, and we have the CNM, Centro Nacional de Microelectronics in Spain, the Fondazione Bruno Kessler, FBK in Torino in Italy, and the Hamamatsu Photonics, so HBK in Japan. Over here we have one prototype designed by CNM, and you can see the structure N++, P+P, where the N+ is in ohmic contact with the cathode ring, and the P+ work as the gain layer we were talking about. This allows to have a really high electric field in the bulk. That means that we're going to have a sharp rise time, and the resulting time resolution will be of the order of 20, 30 picoseconds for a minimum ionizing particle. Now, the choice of the sensor is not the only thing that influences the precision of our detector, but if we analyze the part that actually depend on the sensor, we can point out that the jitter and the Landau fluctuation. So while the jitter is the variation in time caused by the noise of the system itself, the Landau are just due to the stochastic fluctuation of the energy loss through the path inside the bulk. And these two can be, let's say these two problems can be solved or mitigated. Over here, we can see the jitter first that affects the intrinsic rise time because it's due to noise fluctuation. We can try to solve by reducing the sensor thickness but maintaining the same gain so that we have the same pulse height but a faster rise time. But at the same time, decreasing the thickness of the sensor, the Landau fluctuations start becoming dominant. So at the same time, we have to increase the gain and then post-processing the data in a smart way, and we're going to see it in the next few slides. Just to give you some example of the results achievable with this type of detectors, here we have a slide that is dedicated to some of the results obtained by one of the test beam that we collaborated with CMS, and is for the installation of the new MIP timing layer in the barrel of and in the end caps of the experiment. In this case, CMS has, like I was saying before, has super stringent requirement. We are talking about 40 picoseconds of time precision for the whole duration of the life of this sensor. That means up to really high ionizing dose. I think at the end of the lifetime, they're expecting to collect around more than 10 to the 15 neutron equivalent per millimeter square, per centimeter square. And on the right over here, we have one of the plot generated during the test beam that displayed a really nice time resolution, talking about around 26, 27 picosecond for high energy protons. We're talking about 120 GeV and up to moderate rates. Some of the detectors that we tested are the one that I was talking about before, where we can use carbon insertion to control the annealing of the detector, so we can recover the functionality once the sensor is actually irradiated and the crystal is displaced, basically. And here we have some of the results for a detector that is never, a new detector, let's call it like this, a detector that is irradiated up to 10 to the 14, and one that is irradiated to 10 to the 15. And you can see that modifying the bias voltage or the electric field inside the bulk, we can recover some of the precision. If we want to talk about time precision, we can't avoid talking about the readout and the front end that are incredibly important part in the developing of a proper timing detector. So if we take a look at the part that depends on front end readout, we can talk about the jitter again. So we already defined it before, but I had to talk even about the distortions or drifts that are the variation in the amplifier chain response due to the change of the work point of the electronic. On the right here, I decided to put a simulation of a classic high bandwidth amplifier that is usually used in these cases for this kind of the detector, and you can see that the signal to noise ratio depends on clearly on the noise of the system, and the noise of the system depends on the bandwidth of our amplifier. So it's a sort of a cycle. We want to use something with a high bandwidth to resolve fast pulses, but then we keep on inserting white noise in our detector. At the same time, the choice of a front end is crucial to control the rise time and to control the jitter contribution. As you can see over here on the left, the jitter is strictly related to the rise time. And the rise time depends, the bottleneck of the rise time is usually not the sensor itself, but the bandwidth of the sampler that we use to collect our data. So all of these pieces have to, let's say, cooperate together to develop a detector that can be used for proper timing measurements. A last part here of this chapter is dedicated to the post-processing of the data, because you can imagine that the algorithm of reconstruction plays a big role in the precise time measurement, especially because we want to get rid of effects such as the time walk, that is probably the most famous. That is the incorrect reconstruction of the particle timestamp due to basically to simultaneous pulses passing through the detector, but generating signal with different amplitudes. And you can see that if I choose a static threshold over here, these two pulses that in theory are passing through the detector at the same time, gonna have two different timestamps. So how do we correct for that? Well, to correct for that ambiguity of the measurement, we can use a post-processing algorithm. And probably the most famous and the most used is what we call the CFD, constant fraction discriminator. In the constant fraction discriminator, a constant fraction discriminator uses that records, let's say like this, the particle crossing only if the pulse amplitude is greater not than a static threshold, but then a certain fraction of the maximum of the amplitude. So it indirectly generates a dynamic threshold that is tailored for each one of the pulses. Over here, I'm not gonna explain this, but it's just like an analog interpretation of the constant fraction discriminator. But let's say like this, the thing that we have to know is that we can always find the crossing time of, let's say the zero cross time of our signal using the parameter calculated by this part of the algorithm. Let's now go to the center of the discussion, that is the collaboration with the University College Dublin and the St. Luke Hospital. And everything started because actually Nicola developed an electronic board that was used during the years for testing our sensors, so electronic testing and timing resolution testing over a variety of sensors. Usually we use LGADs or Diamond, like you were quoting at the beginning. And these are just a plug and play hybrid board. We call it hybrid because it hosts the sensor over this golden pad that is the basically is the polarization circuit, and it hosts the amplification chain as well. You can see here the two stages of amplification for each one of the channels. It is made by discrete component, like you can see, so that we can change and tweak the parameters of the board to obtain the optimal, to optimize them to host like a certain type of sensor or perform a certain type of measurement. So the two stages of amplification are made by transimpedance amplifier that are rapidly described over here. It's just a design that convert a current input into a voltage output, basically. And the input resistance somehow decides the whole the gain of the amplification stage. What we need to know for our case is that increasing the input impedance, the signal becomes bigger, but it gets slower. That means the integration time will be longer. But we know that we have discrete components, so it means that if we just change the input impedance, modify the input impedance, now we have a fast rise time, a really fast signal, maybe with a worse signal to noise, but that's not what we want to use in a second. Here you can see some of the performance that were already collected during previous tests. In particular, this one is summarizing this publication over here. In this case, the board was optimized to work with the minimum ionizing particle and to work as a really precise detector. And you can see that using 180 GeV pions beam at the CERN North area, the detector showed really great performance in time reconstruction. We're talking about 27 picoseconds of time precision at the bias voltage that is slightly bigger than 220 volts. Well, what is the idea then? What is the idea of the collaboration between KU, our group, and the University of Dublin? Well, we wanted to solve a problem. The problem is that during the standard radiological exams and diagnostic procedures in medical physics, the differential dose provided to the patient is measured using gas detectors. And that in per se is not a problem, but the measurement relies on the integration over time of the charge produced inside the active volume of the detector itself. So intrinsically, this procedure can keep track of the fast variation of the particle fluxes inside the detector itself. Over here on the left, we have just like a schematization, a cartoon of how the two detector, how to expect like the detector response from the two. But in the case of, for example, a charged particle beam, the dose absorbed can be obtained integrating this formula over here. So the idea was, what if we can develop a detector that is fast and efficient enough to actually count this parameter over here that is called fluence or fluence rate. So instead of integrating the charge and searching for the dose that needs calibration, needs, well, you can do it with an ion chamber, so we wouldn't need our detector. But what if we want to see, actually count the particle? What are the pros and the cons of the measurement? For sure, it's an extremely precise measurement because I'm just counting. If I can obtain a detector that is fast enough to have single particle resolution, I can actually count, and a counting experiment is way more precise than the integration, just integrating the charge. There is no need for energy calibration because I'm just counting the particle. Also, an important part for medical physics is that the spatial resolution of or the granularity of silicons can be reduced to even like millimeters, a millimeter square. Now we have some cons over here. For sure, the problem is that we can't use our silicon for photon spin because we can use it, but the efficiency of photoconversion is really low, and it requires way more computing power and way more technology, let's say, behind it. So what we decided to do is that the collaboration between the University of Kansas and the College of Dublin organized a week of data dating using a dismissed LINAC machine that was provided by the St. Luke Hospital in Dublin. And we wanted to assess the capabilities of single particle resolution of an LGAD. So the electrode over here, you can see it in the picture, the LINAC is called electrode modality is elect as the brand. And everything that we need to know is that the pulse structure, the nominal pulse structure over here. So the pulse length, the nominal pulse length is 3.2 microseconds, but each one of these cycle has 1,000 of 30 picoseconds sub-pulses that compose the LINAC cycle itself, and they're separated by 350 picoseconds. So we never use the machine as a photon source, like I was saying before, but use it as an electron beam so that the efficiency of our detector is going to be almost 100%. The electron beam providable is the LINAC can provide is the energy can go from 4 to 18 MeV with dose rate up to 600 a minute, and the pulse repetition frequency that is 200 hertz. So the 5 milliseconds between the in the spacing between the cycles. What was our setup? Well, the device and the test here was always compared to a detector used during standard medical exams. There was a PTW semiflex ion chamber. There is just a cylinder, basically a cylinder of radius almost 3 millimeters and encapsulated in graphite and PMMA. On our side, we had our LGAD that was previously test, like I was saying. This is the design of these LGADs was made to reconstruct the passage of protons in the CTPPS experiment. So the geometry is not the most optimized, but the pixel active area that we use was around 1 millimeter square. The thickness of this sensor is 50 microns, and the time resolution under this condition is around 50 picoseconds. Here we can see a screenshot of the sampler used. It was just an oscilloscope with a bandwidth of 1 gigahertz and a sampling rate of 4 gigasample second. So in here, what you see is a single LINAC spill, that is this encapsulating this 2.34 microseconds from the beginning to the end of the particle, the incident particle in the detector. And on in this purple one is what we call the tyrotron. So that is the electron injection inside the first acceleration stage of the machine. And this was used as the trigger to trigger our acquisition. So every time that the electron were injected, we were opening a window and we were collecting everything with that time window. Now, the detector was mounted on a moving support. It was encapsulated in this PTW 3D scanner water tank that is usually used for the PTW semiflex ion chamber, and was basically aligned using the in-room lasers and the LINAC light field crosshair, basically. This can move in all the directions, X, Y, and Z, but our data will be presented as just the scan of the X-axis. So the only position that we changed was on this axis, in the red axis. Now you can see that here the trajectory of the electron beams, because we were talking about electrons, is bent. That's because we use a permanent magnet below here the collimators, the multi-leaf collimators of the LINAC machine. You can see here in the cartoon. So we could isolate the charge and neutral components. When I say that, like you can see over here in this plot, that is the plot obtained using the ion chamber, that around the central position underneath the LINAC, we have a bump on excess in data. And that's probably due to the Bremsstrahlung photons that we are creating in the interaction with the, when the electron interact with the air, basically. Each one of basically, you'll see later, but for each one of the measurement, we always try to average 200 pulses of the LINAC, so to keep it coherent during the whole data acquisition. So what is the first measurements that we can actually do? Well, it's let's call it the easiest, is the one that we can directly compare with the ion chamber. So we can integrate the charge collected by our sensor, and extract an idea basically, and then compare it with the ion chamber one. Now, if here we have a simple event monitor, and you're gonna have like some curves superimposed but overlapped in that. But now let's talk about this green part over here. In this green part over here, we can obtain a couple of parameters that we'll need for our charge integration. First of all, what is the DC offset that we have? So what is the baseline correction to operate at the beginning of our algorithm? Well, we averaged from 0.5 to 1.5 microsecond before the pulse for each one of the waveform, so we can have an idea of the DC offset. At the same time, in the same region, we can calculate the RMS, the root mean square of the signal, so to have an idea of the noise of our detector. So over here we have a diagram that try to illustrate what is the functional, like how the charge integration works. First of all, we have the baseline correction. Second of all, we have a pulse site. Basically, we add every sample. You'll see later, but in a certain range of value, but we just add all of the values that we have, all of the pulse site, and we iterate this for every trigger. So after our 200 triggers, the average and the RMS are then plotted for each one of the detector positions. So to summarize this, the charge collected is estimated by adding the height of every samples from the beginning of the particle spill to the end of the signal itself. And we iterate this clearly for every detector position. But to give a bit of an insight in the charge integrated, here we have the amplifier that is collecting all the charge, and then basically the same charge is injected back in the amplifier since it's coupled in AC. So the total integral of the signal should be null due to the overshoot of the amplification chain itself. But so we had to smartly select the limit of this discrete sum in this case, and in our case the maximum of this distribution work as our upper bound. Here we have the results as displayed from the plotter. On the right, we have the charge recorded in the LGAD compared to the ion chamber as a function of the distance from the beam axis. So you can see here the axis, the photon axis, and then the two curves are pretty much overlapped, clearly with a different normalization. We don't have a calibration of the LGAD, so we don't know. We can't plot it if not in arbitrary unit. The principal differences that we observe in the whole spectrum is when we have a large flux of photons, sorry, because more photons probably may be interacting with the casing of the gas detector itself, instead of the metallization of the silicon. While the rest of the spectrum can be broadly similar, and that is confirmed when we plot the correlation between the two quantities. Every point, I didn't say, but every point obtained with the LGAD is the average of the 200 triggers, and the error is just the RMS of that mean. Then we have to talk about let's say the core of our testing. That was a single particle ID capabilities of the LGAD. This time we'll take a look of the center of this signal, just to give an idea of how the cluster recognition algorithm works. So in this case, we first use a low-pass filter with a frequency cut of around 250 megahertz to cut the high frequency fluctuation, and then we go inside this data smoothing loop. And this data smoothing loop, basically, what it is just pedestrian removing. That means that it's a moving average that depends on the position of the clusters themselves. So we average the data from 0.5 to 1.5 nanosecond before every pulse, and we use that as our moving average. So once the data are smooth by the low-pass filter and the pedals are removing, we can go actually in our final cluster finder algorithm that gives the number of cluster and the average number of cluster for each detector position. When I say cluster, I mean like the pulses. So the passage should be the passage of particles in the detector itself, but gives information about the time of passage itself. And even this one is iterated over every trigger and iterated over every detector position. So if you want to take a closer look at the cluster finder algorithm, the condition here, you have an event monitor after the data smoothing, and you see that I zoom in this red area over here, and I just highlighted all the peaks that were recognized as a particle passing through the detector by the algorithm. Now, to be accepted as a pulse, as a particle, the algorithm has to basically fulfill a series of conditions, and those are the discrete conditions. The first one is that the signal exceed by 5 sigma the noise level. In volt it was around 8 millivolt. Second point is that the peak is isolated. That means that the algorithms will reject at least one if peaks are closer than 3 nanoseconds to each other. And then we ask for a 10 nanosecond separation between consecutive peaks. This goes the average integration time of the signal of our detector in this condition is around 10 nanoseconds. This is really performant for isolated peaks, since the signal to noise is really high with these 6 MeV electrons, but the efficiency drops as the time spacing between consecutive peaks start narrowing down, basically. So if it gets significantly lower than 10 nanoseconds, then I start losing the single particle identification capabilities. And you can see even better from here. On average, the algorithm fails when 2 particles pass through the detector within 6.5 nanoseconds of each other. And the probability of that occurring is the exponential of that, just that time of the detector, basically. The effects can be seen over here when the fluxes become bigger. So at the peak of this distribution, we start losing some signal. So basically, counting particle gives equivalent results to integrating a charge, but the LGAD is operating as a single quantum detector. That means that each one of these measurement is performed in microseconds. Each one of these of the ion chamber is performed over seconds, if not tens of seconds. And if the rate of incident particles is smaller than 200 megahertz, we verify that the LGAD, our detector, resolves single electrons with a time resolution of about 50 picosecond. That is precision with which we can reconstruct the leading edge. That being said, once we demonstrated that, we say like, why stop here? Since we already have the information of the timestamp of the signal, why not try to characterize the LINAC response itself? Because we have a nominal feature of the LINAC, but it's really difficult to verify if the pulse is exactly 3 microseconds, as if the substructure is actually present. So the first important feature of the basically that we wanted to calculate is the LINAC spill effective duration in time, and the distribution of particles over time, emitted over time. So over here on the right, we have the distribution as a function of time for the clusters, so for the timestamp of the clusters. On the left here, we have just a plot where we were trying to evaluate the average duration of the spill. Once we sum together every, we do the same, let's say, for every detected position and for every trigger, here is what we have. And clearly, the number of particles is related to relative dose delivered, so we can plot it as a function of it. And to our surprise, the width of the pulse seems to be smaller than the nominal. And we found out that instead of more than 3 microseconds, the whole duration is around 2.85 plus or minus 0.01 microseconds. We didn't want to stop there. We wanted, since on paper, our detector has a time resolution of 50 picoseconds, the sub-pulse structure of the LINAC cycle, if you remember, every LINAC cycle was 3 microseconds, but thousands of 30 picoseconds long, 30 nanosecond long, sorry, pulses. So we could try to resolve this structure if our detector actually had a 50 picoseconds time resolution. Main problem for this is that the trigger that we were using, in this case the Titron, has a huge jitter that is actually the bottleneck of our measurement. So first of all, we decided to plot the distribution of timestamps, basically, for consecutive particles. Even here, the effective behavior is expected to be affected by the inefficiencies when 2 consecutive peaks are clearly closer than 10 nanoseconds in time. And then, as a first, just trying to verify if you can see a periodicity in our signal, we can try to see the substructure just plotting the remainder of delta t with 1.75 that is extracted by the cycle of the LINAC, basically. And here you can see in this plot, number of clusters as a function of the remainder, you can see that we start to see a periodicity in the signal. So we were really excited of this result, and we tried to investigate even more. To have like a proper measurement of that, we decided to work with the autocorrelation. And the autocorrelation is just the correlation of a signal with a delayed copy of itself, plotted as a function of the delay. So it's basically, it's just a convolution. In this case, it's you can see over here, is just a discrete convolution of the signal with itself. And what we see is that basically that coarse grain structure that we see here in the delta t basically results in a exponential shape superimposed to a fine sinusoidal pattern. Now over here, or the autocorrelation is plotted after the exponential dependencies was removed, so you see only the fine sinusoidal pattern. Once we managed to verify, it wasn't easy, the period of this sign, we noticed that the period came out to be 346 plus or minus 3 picoseconds. That is exactly the spacing between the 30 picoseconds of pulses. So it's consistent with the nominal frequency of the LINAC of almost 3 gigahertz. So this is probably the most unexpected and best success of the publication itself. before stopping, I want to just like give a couple of slides about the next step. So the improvement of the current technology and how to expand the horizon, let's say, of applications. First of all, there is something that directly we can let's say aim to directly do with our detectors. That since we know that the detector can be used as a single quantum detector, we could actually start using the KU board as a particle counter in low dose release, basically, or provided if you want. Here we have one test that we actually performed during the doubling test beam. We have a artificial hip, and the X-rays were just scattering from the hip, and we try to interpolate, let's say like this, the amount of radiation that is backscattered by artificial limbs and joints. There is a problem here. The problem is that we have to have a full picture of the setup. So we need a full simulation of the LINAC and the interaction of neutral particle with air before colliding with our detector. But it's something that we can work on. Other groups started publishing about use of LGADs for soft X-rays detection. So new generation LGADs have been used to try to work as a single quantum detector in not single quantum detector, to work as a detector for photo detection. In particular, these are the result obtained with 50 micrometers LGAD used as a slug with photons in the range of, or X-rays in the range of 616 keV. And the LGAD demonstrated an optimal time resolution, honestly, for photons that is 100 picoseconds, and a single pulse resolution with 2 nanoseconds beam separation. Now, I don't know why I lost the arrow here, but these are spaced by consecutive peaks are spaced by 2 nanoseconds. Also, they demonstrated that the response of the LGADs to photon from different X-ray transitions over here can actually resolve pretty well or can actually work pretty well as a energy discriminator, basically. Really important for the medical aspect of the studies is that right now several recent studies try to demonstrate the benefit of increasing the dose rate delivered by the medical LINAC. So there is the instantaneous dose delivered to the patient. This technique is called flash radiotherapy, and for this purpose, the standard medical LINAC accelerator are converted to deliver particles at a really high rate. All of this comes from studies that were performed in the 60s that is about the tissue toxicity that reports that healthy human tissues were less affected from higher instantaneous doses compared to the standard ones in radiotherapy. And at the same time, the effect on the cancerous cells is actually not independent from the rate of radiation delivered. So we have basically increasing signal to noise or benefit counts of the diagnostic exam or the exam itself. Possible causes are some possible causes of this, or if you're interested in this link over here, but it might be the since hypoxic tissues, so tissue that are deprived of oxygen are more resistant to radiation. The level of hypoxia at ultra high dose rates and subsequent radioresistance transfer to the tissues that are irradiated. So it's basically it's a system of self-defense, if I call it like this. Same thing about the immune modification. Since it's like the same dose is delivered in a shorter time, the response of the immune system is not as efficient. So it doesn't change the effect on the cancerous cells, basically. But what is the current technology that is used to monitor this beam? It's just usually it relies on self-developing radiochromic films, and those can be read out only when the dose is already delivered. And exactly like the ion chamber, basically we have an integration of the whole signal, and we can resolve the structure of the beam. But as you said in Giuseppe Felici's et al. Publication over here, the dosimetry under flash conditions remain a really challenging task. So this is a field that could be interesting for application of fast timing detectors. Some other applications can be clearly a direct consequence of the studies is the use of sensor for hydrotherapy. So medical facilities that instead of where the cancer basically cells are treated with the hadrons, so with protons. And for this, we have a couple of design here that actually Nicola provided. These are thin LGADs, as you can see here in the HV pad. And you can see that the material budget of the PCBs here is reduced by basically by cutting the PCB underneath the sensor itself. To conclude, I decided to divide it even here so you can keep track. In clearly the recent results in timing detector show incredibly promising performance, and the demands, basically strict demands of high energy physics, are keep on pushing the production. And the choice of this sensor combined with the readout and a fast sampler, basically you can develop detectors that are quite performant, and they can produce signals that are as precise as short as a few nanoseconds, and timing resolution that are as precise as tens of picoseconds. During the test beam, the QA detector proved to be able to replicate the results already obtained with the ion chamber in a much shorter time scale. We're talking about, as I said before, microseconds instead of seconds. Also, the LGAD displays like single particle identification capabilities up to high rates using an electron beam. The other interesting thing is that the capabilities of the LGADs actually open the possibility for the study of the beam profile. So to characterize the machine itself, that is something that is usually not as easy just using integrating detectors. Last but not least, we have the last chapter, and where I point out that the demand requests coming from high energy physics experiment accelerate the production, as I already said. In terms like basically broaden the spectrum of application collaterally. Also, I wanted to point out the interesting result can be found in testing the sensor, this type of sensor, as a beam monitor in hydrotherapy, and even in flash LINAC machines. And this is let's say the medical interest of the studies. So thank you a lot for your attention, and if there are any questions.
Hi, Tommaso. Yeah, so just a very general question about the timing detectors themselves. Can you go to slide 8?
8, absolutely. Here.
Yeah, I'm just curious. You said that for a scene detector, the biggest contributor to the uncertainty would be Landau fluctuation. So would it mean that the distribution of the time would be a little bit asymmetric? So like Landau itself, or everything is just smoothed by like other factors? Or
you mean the distribution of energy in the bulk?
No, like the time itself, like the distributions that you have in the next slide, slide 8.
Okay. This one over here.
Yeah.
Well, this is a difference of time of arrival between the detector and the reference itself. So you have to keep that into account. That is not the pulse height distribution or the shaping time. This is the difference of timestamp between UFC detector and MCP. Basically, they usually have an intrinsic lower precision, so we can rule it out of the equation. And it should be distributed as a Gaussian, and then the sigma of this Gaussian is going to give you the precision, basically.
Okay.
So yeah, I know what I understand what you're saying, but I think that you can see the effects in the probably in the pole side distribution. Sorry, the distribution, or in the rise time distribution. Sorry.
Okay. Yeah. Thank you.
Hi. Thank you for the nice talk. I had a question. Maybe I missed it, but in those plots with the integrated charge
Yes.
versus position, I was wondering why the maximum, the peak is not on the beam axis and it's there around 20, 25.
Yeah. So yes. So at the beginning here, maybe I should have said like, so we are using an electron beam. In order to not have the contamination of the neutral particles that we create when the charged particle interact with air, basically, we decided to put a magnet over here so that all the charged particle contribution would be displaced with respect to basically to the center of the beam itself. So now we have all the central that are going straight down, all the charged particles that are bent to a certain direction. So this was going to be position 0, for example, and this would be position 22, basically, out of the beam.
Okay, sorry. I didn't get it.
No problem.
Nice. I see that there are no other questions. Just if you want to give us an idea of what can happen in the future, what is the next development with these kind of sensors? I
think it will be, first of all, we tested the same detector in here in a facility in LINAC at the hospital in Kansas City. Clearly, unfortunately, in this moment, everything is locked, so we can access the facility. But first of all, an interesting part would be to further the studies on LINAC to see actually the capabilities to even higher rates and to verify the possibility to work in flash LINAC condition, flash radiotherapy condition. Second of all, I think that since all of these detectors were originally thought for protons being hadron beams in high energy physics, in particular these ones were for CTPPS. I think that the hadron therapy will be the next, important step to do, to perform tests over hadrons.